Hello and welcome to Tech Simplified TV. Today we are back with another technical topic from backend of VLSI design flow. In VLSI, design and verification both are equally significant. Every design must clear verification steps. In backend, LVS and DRC are two such verification steps. We already have one episode on DRC or design rule check. Today we will discuss about LVS, that is Layout Versus Schematic. We will also discuss about a force tool intended for LVS, that is NETGEN. If you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and LVS. Next, basics of LVS. Third, process overview and challenges. Next, layout versus schematic flow. After that, LVS issues and debug. Next, about NETGEN. NETGEN is a free and open source tool for LVS. In this episode, now with basics of LVS, we will also discuss about basics about NETGEN. After that, significance of Setupfile. This Setupfile is absolutely connected with NETGEN tool running. We will discuss about its importance, what does it mean, significance of Setupfile. Next, what is valid file name? Whenever we will encounter some command of NETGEN, we will see in many places valid file name is used. We will try to understand what is valid file name with respect to NETGEN. Then NETGEN command types. First, running NETGEN. These are the commands which are used to run NETGEN. Next, netlist manipulation commands. And third, netlist comparison commands. So these are the pointers we will cover in today's episode. Now let's move to the next slide. Design flow and LVS. So this is the standard design flow. Starting from design specification, then RTL coding, verification, synthesis, DFT. And after that, it's entering backend from flow planning, partitioning flow planning, power planning, global placement, detail placement. That flow planning, power planning, we have already done partitioning, and along with power planning, pin assignment is also done. These are the steps: global placement, detail placement, clock tree synthesis, we have done it. Global and detail routing, layout generation or changes, and next comes DRC and LVS. This is basically backend verification. DRC and LVS, always we heard these two terms very closely. Always it's uttered together. DRC means design rule check and LVS means layout versus schematic. These are very basic and important steps of backend verification along with EM and IR. So these two steps, in most of time we heard this DRC and LVS, these two terminology together. Today we will discuss about LVS. We already have an episode about DRC. Link is in the description. Watch it or read the article. Both the links are provided in description. So today we will talk about LVS. So in nanometric era, designs are becoming more complex and chip sizes are growing. Know that? To make sure design is correct, larger layout databases need to be checked during physical verification process within the same tight project timeline. It's a competitive market and we have to launch our product within predicted time, otherwise we might lose the market. If an error is found after the design is built, it will lead to costly mask changes and delays in releasing the SoC. We need to check, we need to make it sure that whatever we intend to do here, that is when we do a design specification, we have certain target in our mind that we want to achieve this kind of performance. That and that should be get done by our chip. Building the mask is a costly affair. Time-wise, material-wise, it's very expensive. Before tape out and before making the mask, we have to make it sure that whatever design we are taking towards tape out exactly representing what we have intended here. That means design specification is perfectly translated into the mask or layout. LVS is one of the way to take it. Physical verification ensures that the design layout matches the schematic and changes if the layout follows manufacturing rules from semiconductor fabrication labs, ensuring it can be produced correctly. There are some rules. When we have a design, we have a layout, it's good. Although, since we are following a technology node, According to a technology node, when it is going to get fabricated in foundry, it has to follow some rules. These are the rules. We cannot change it. These are the unchangeable rules set by foundry. These are basically design rules. In DRC step, what we do, we check whether our layout, our design we have done is following that guideline. We cannot break all those rules. Otherwise, it will create problem while manufacturing. DRC are the checks if the design layout follows the rules needed for it to be successfully manufactured by the fabrication lab. We have to follow it. Although it doesn't mean that layout is doing exactly what we as intended in design specific. We do it in LVS. LVS verifies that the design layout works the same way as the schematic of the design. Yes, it does not guarantee that the layout will work as intended. It only checks if the layout follows the fabrication rules for error-free manufacturing. ERC focuses on ensuring the layout can be made correctly, but it doesn't confirm that the circuit will perform as expected. The need for LVS came from this limitation, as LVS checks if the layout matches the intended circuit design. From here, we can understand what are the importance of DRC and LVS. Both are important for successful tape out, and since we have already discussed DRC in some other episode, here we will concentrate about LVS only. Next slide. Now basics of LVS. A EDA tool performs LVS using a set of code instructions. Those set of instructions are LVS rule deck. LVS rule deck guides the tool by providing necessary instruction and identifying required files for the process. So obviously LVS is done by so many proprietary EDA tools from famous EDA vendors. Now we have another tool which is free and open source. We don't have to pay for it. That is NETGEN. So here we will use NETGEN for LVS purpose. There are so many tools are used in industry. Those are industry standard, and also in NETGEN has a standard. We will discuss it later. That is quite good for our study purpose, our practice purpose. It's quite good. So we have chosen NETGEN. Now LVS is done in 2 steps: extraction and comparison. We understand that when we need to check whether the layout is working as per the schematic, there is a comparison. There are 2 steps: first extraction and comparison. Design inputs needed to run LVS include GDS layout of the design, schematic netlist of the design, cell definition file including IP files and standard cells, pad reference file. The GDS layout is required. From there we extract a netlist. That netlist is compared with schematic netlist of the design. Both are compared. The LVS rule deck is written in formats like SVRF, standard verification rule format, or TVF, that is technical verification format, and helps the tool extract the devices and connections of the circuit. It defines the layers used in the layout and matches layer descriptions to their locations in GDS file to identify electrically connected regions known as nets. The rule deck also includes definitions of the device structures. This is the basic knowledge about LVS. Before we start studying LVS, we need to know all these are the prerequisites we required. We are done with this slide also. Let's move to the next slide. Now process overview and challenges. Now process overview. Circuit designers create a schematic using fundamental devices like resistor, transistor, the basic components we use in our circuit. Circuit designers create a schematic using all these fundamental devices. The schematic is converted into netlist, that is SPICE format. For simulation and comparison, we already have a series of SPICE. Watch that series. Link is provided in the description box, playlist of SPICE. Watch that. When we will discuss about netlist, we need to understand which part of the netlist which is written in SPICE format means what. So for that, watch it to understand properly. Now layout engineer generate a layout based on the schematic, considering placement, sizing and design rules. The layout is extracted into a netlist, which should represent the same circuit as the schematic. The layout is extracted into a netlist. So one netlist we get from layout, and another is from same circuit as the schematic. So we have to compare these two. Purpose of LVS: identify error introduced during layout process. The schematic is usually assumed to be correct because it's used for simulation. The LVS is essential for checking manual correction or verifying automated layout synthesis. What are the challenges? Challenges are errors in layout or synthesis can create incorrect circuits. LVS helps pinpoint these issues. Full chip verification through simulation can be time consuming and complex. So LVS is a quicker alternative. Full chip verification is a step and it's get done. Post simulation is a process for that. So we are done with this slide. We will move to the next slide. Now layout versus schematic. This is layout, netlist expected from that. It is schematic, netlist, extraction and comparison, LVS report and analysis of the result. If it's matched netlist, then finished. If not in unmatched, then there should be some change done the layout. So LVS flow work in two major phases: extraction and comparison. Extraction phase, verification tool takes the GDS file and breaks it down into basic design components like transistor, diodes, capacitor and resistor. These components are identified by recognizing the layers and shapes in the GDS file or by using cell definitions from the IP blocks or the LVS rule day. The tool also extracts connectivity information between these components from the GDS file. GDS file is full of geometrical structure. All the devices and everything is represented. That is layout basically. So represented with geometrical structure. Layers after layers after layers. So extraction of information is done from those layers. So during connectivity extraction, each electrical net is given a unique node number for easy identification. Otherwise, it's not very easy to identify. They look all same. Color code is only used there. All look same. Layers after layers. So unique node number is given. Net names can also be assigned based on text object in the layout or control file. This device and connectivity information is written into layout netlist file is called the layout extracted netlist. The step is known as extraction. Now what is comparison phase? The verification tool compares the electrical circuits from schematic netlist and layout extracted netlist using the LVS rule day. After a successful comparison, a one-to-one match between elements like instances, nets, ports and pins in both netlists is established. The goal is to ensure the layout accurately represents the functionality in the schematic. If the netlist doesn't match, discrepancies are reported in an LVS result database, listing issues like incorrect nets, ports or instances for debugging. The verification tool prepares net to net, port to port, pin to pin, one-on-one match between elements. It's done. If the netlist doesn't match, discrepancies are reported in the LVS result and we have to work on that. Like how many incorrect pins or ports or instances that is reported, we have to debug based on that. So we are done with this slide. LVS issues and debug. Now let's try to understand what are the common LVS issues. The source SPICE netlist would match the SPICE netlist extracted from layout. That is the core of LVS. Now, what are the common LVS checks we do? That compare the number of devices in both the schematic and layout. Number of devices. Check the types of devices in the layout and schematic. Compare types of devices. What types of devices are there? Resistor, capacitor, transistor, all. So, compare the number of nets in the schematic and layout. Compare the number of ports, connectivity issues, ambiguity points in the designs, cell comparison. These are the common LVS check. And what are the common LVS issues we face? Short between different NIC. Very common. Power short. There is a representative diagram we tried to show here. That is a power short. Another one is power open. Similar type of power line, although there are gaps. So that is power open. Now power short with signal. Multiple wires that should not be connected together become connected. Those wires which should not get connected to each other, they get connected to each other. Now signal open. Wires or components that require to be connected are left floating or partially connected. Deleted instance. Accidental deletion of some particular instance that should be there, it's got deleted. So when we are checking or comparing one to one, then in one point we will find that one instance is less. So there is something missing that will get reported. Now missing will tap. Tap cells provide a substrate connection NVL to VDD and piece up to VSS. So that means if NVL is used for a connection, missing will tap means basically discontinuity in connection. Overlapping filler cells, missing filler cells. Since filler cells provide power or ground and NVL continuity, missing filler cells will result in power or ground opens between standard cells. Filler cells missing, overlapping filler cells, missing well tap, all this will create discrepancy in the design and that will get reported in the LVS. These are the most common LVS issues. Short, power open, power short with signal open, deleted instances, missing well tap, overlapping filler cells, missing filler cells. These are common. We are done with this slide. We will move to the next slide. Now NETGEN. In first 4-5 slides, we have already tried to discuss about basics about LVS. Theoretically. Now we will try to understand basic of a tool which we are going to use for LVS. That tool is NETGEN. Now let's know about NETGEN. So the first thing is NETGEN is a free and open source tool. And you can find all related information at this link is provided in the comment section. Click and go there and read all the pages. It's a very good site, very good website. NETGEN is a tool with two main functions: convert netlist between different formats and compare netlists to check if they are equivalent or identify differences. So that is LVS. Netlist conversion, simple process in most netlist formats are similar. Netlist comparison, LVS ensures that a VLSI layout matches the original schematic design. NETGEN version 1.5 is considered complete and competitive with commercial grade tools. NETGEN version 1.5.76 completes the major development of NETGEN as a commercial grade tool. All remaining revisions will be bug fixes or minor enhancement. NETGEN was written by Massimo Civilotti and eventually incorporated into the beginning of Tanner L-Edit suite of tools. However, the original code was left open source, so it has been incorporated into Tickle-based suite of tools like Magic, IRSim and Xcircuit by Tim Edwards, the owner of Open Circuit Design domain. So this domain is owned by Tim Edwards and our special thanks should go to Tim Edwards. Thanks Tim. Linux and Windows compatible versions are available. In this location you can find this. Here we will work only with Linux version. Although both are present, here we will only work with Linux version. This is about basics of NETGEN. Now let's move to the next slide. Significance of Setupfile. When we will run NETGEN, Setupfile is used there. So what is actually a Setupfile? This is the command NETGEN, then LVS, circuit1.spy, circuit2spy and setup.tickle and log file. Log file name can give as per your choice, you can give it its name. That setup.tickle, that is one argument. What is actually setup.tickle and what does it do? Let's understand that. A Setupfile in NETGEN is used to provide additional instructions or configurations for LVS comparison. It is written in tickle syntax and typically contains commands to handle differences between netlists such as mapping device models or sub-circuit names and defining pin permutations. Later on, when we will take some examples provided in the website and try to understand, so that time we will see Setupfile is used in those examples. Whatever we are mentioning here, that additional instruction or configuration for LVS comparison, that in real time we will do in later episodes. It is written in tickle syntax. Tickle is a scripting language. If you are in VLSI domain, be it front end, be it back end, you definitely need to know Tickle. We have a very good series on Tickle, very popular. Both individual episodes are there in a playlist and marathon is also released. Links are provided in the description box. Go and watch. Typical content of a Setupfile. Mapping subcircuit or device class name. Equate classes, name 1, name 2. This we can provide in the setup. In permutations, permute transistors, permute pins, valid cell name, pin 1, pin 2. Black box declaration, model black box on. Global node declaration, global valid cell name, etc. Ignoring specific device classes. Ignore class, that custom property settings, permutations control, that is optional. Permute forget valid cell name, pin 1, pin 2. Keeping flattening of specific cells. Usage of Setupfile in LVS. The first time you will see is why we will run. If no setup file is provided, NETGEN uses the default file setup.tcl if available or runs without custom configuration. This setup file helps resolve discrepancies by mapping equivalent elements, permuting pins, and managing hierarchical comparisons. Setup file is provided and we can list additional instructions there as per our need. Let us see in some later examples how we use the setup file. So this is about setup file. So we are done with this slide and now let's see. So what is valid file name? In NETGEN, valid file name refers to the name of a netlist that is correctly formatted and recognized by NETGEN for reading or comparison operations. Valid file name is used when interacting with netlist or identifying special files in commands. Context and usage of valid file name. Top level cell matching. If a netlist file contains a top level cell, the file name is treated as equivalent to the top level cell's name. That is circuit.spice, top level cell is circuit. Syntax for identifying cell using file names. When a netlist contains sub-circuit definitions, you can use both the file name and the specific cell name to identify and compare cells. This ensures hierarchical comparison where sub-circuits are compared at a specific level. It is file name, cell name, file name to cell name to. Command example using valid file name. Printing all known cells in a specific file like cells on valid file name. Flattening specific files. NETGEN allows you to flatten a hierarchical design by specifying the file name like flatten valid file name. Now handling files with standard extensions. NETGEN automatically detects files based on common extensions like spice, .sim or .spc. So valid file name refers to the name of a netlist file that correctly formatted and recognized by NETGEN for reading or comparison. That is valid file name. Now we will move to the NETGEN commands. There are three types of commands. One is NETGEN invocation commands, netlist manipulation commands, and netlist comparison commands. So NETGEN invocation commands is basically how to run NETGEN. First, running NETGEN. Command line invocation. If we write NETGEN with no arguments, NETGEN will bring up a TK console window with an interpreter prompt waiting for command input from the user. And if we type NETGEN no console command line, then with argument no console, there will be no console window and the interpreter prompt will be in the terminal. No separate interpreter prompt will come. NETGEN LVS circuit1.spice, circuit2.spice. For batch mode processing of multiple commands, put the command into a file and source that file through the command line. NETGEN source batch script.tcl. Let's create a tcl file with batch underscore script.tcl and write that LVS circuit1.spc, circuit2.spc, Setupfile, log file and save it and source it. It will run. For batch mode processing of multiple commands, put the commands into a tcl file and source that file. Batch script will end by returning the tcl interpreter unless it ends with a quit. And running with tk console, if we type only NETGEN, the tk console will come. That time we have to write in that interpreter prompt or that in console window that LVS circuit1, circuit2, setup and log. It will run. These are the commands to run NETGEN. Next, now netlist manipulation commands. These are second set of command. Canonical valid cell name, return to item list containing the cell name and file number of the cell indicated. Read a netlist. Auto detection, first look for files with standard extensions. If no file is found with a standard extension, then the file is checked for the initial character, which is always star in spice files, and type in .sim. Read lib format file now. Initialize a library module definition where format is one of the Actel, Vice or Xilinx. The library definitions need to be initialized prior to reading any netlist file that is to be written as WriteNet Actel file name, WriteNet Xilinx file name, or a Spice netlist with the definitions from the library included in the file. Basically, these two commands are related to the file type and their extension for valid file type for the tool. Now WriteNet, write a netlist file, flatten a hierarchical cell. We will use it later, flatten class. In this form, the fill command, the full cell database is search for instances of the same valid cell name, which are then flattened by merging them into the parent cell. Flatten we will use later in example. Model valid cell name, declare a cell to be specific model type. Supported low-level device model types are NMOS with 3 or 4 port, PMOS 4 port, PNP, NPN, resistor, capacitor, diode, inductor or X-line. A low-level device can be treated as a sub-circuit by declaring model to be circuit. A circuit declared to be model black box only recognize the pin names and pin order but will otherwise ignore the subcell. If we declare the model as black box, only pins are considered. Nodes, print nodes of an element or cell with option list. There are some option with list. Return a list of nodes to the tickle interpreter. Elements, there is also a list option. Print elements of a node or cell with option list. Return a list of elements to the tickle interpreter. And cells, print known cells. Option all. Print all cells including primitives. If valid file name is given, then restrict the listing of cells to those belonging to the specific file. Quit, exit the NETGEN and tickle prompt and help print basic usage information. You type help in the basic usage and quit with NETGEN and tickle console. So these are netlist management commands. Next, netlist comparison commands. Compare valid cell name 1, valid cell name 2. Declare 2 cells for netlist comparison. Subcircuits that are not declared equivalent or that do not have the same name in both cells are flattened. Otherwise, subcircuit instances will be compared as black box devices without comparison of their content. Compare hierarchical. To a 4 hierarchical comparison, the first cell must declare the 2 top level cells, valid cell name 1 and valid cell name 2. The cell hierarchy will be searched. All cells with matching names or cells that are declared equivalent will be saved in a stack. Global valid cell name net name. This command makes the net name in the hierarchy of cell valid cell name into a global node. The cell valid cell name must exist in the database. It must have already been read into NETGEN. This command is typically used within the Setupfile to assert which node in a file need to be declared global. There is an example of that in later. For instance, if the spice netlist file.spice contains a subcircuit using default spice ground node name 0, then the Setupfile would need the line global file spice. Note that spice netlist file can contain a forward reference to a global node name using the global name card, in which case global statement is not needed. Next, another set of comparison command. Summary. Summarize the internal data structure. Equate option the elements, equate 2 elements. With option nodes, equate 2 nodes. With option classes, equate 2 device classes. Element, node, classes. In all cases, values of cell name 2 are altered to match those of M1. Print commands are there. But there are also options elements, nodes, queue, legal, illegal. Print full report on the internal data structure with option legal, print only legal or matching partitions. And with option illegal, print only illegal or non-matching partitions. With option list, return a nested list with the information. Property fault. This command is implicitly run at the beginning of every LVS run unless the Setupfile contains any property commands, in which case all properties must be declared in the Setupfile. If the intent of Setupfile is to modify default values, then property default should be put in the Setupfile before all other properties. So here also we get a reference of Setupfile. Permute default. This command is implicitly run at the beginning of every LVS run unless the Setupfile contains any permute command, in which case all permutations must be declared in the Setupfile. If the intent of the Setupfile is to modify the default values, then permute default should be put in the Setupfile before all other permutes. There are some versions of permute like permute transistors or resistors or capacitors, permute pins, valid cell name, permute valid cell name pin 1, pin 2, permute forget, valid cell name pin 1, pin 2. With option pin, permute pins pin 1 and pin 2 on device valid cell name. If more than 2 pins may be permuted, this command may be issued multiple times between pairs of pins. With option forget, remove any permutation between pins pin 1 and pin 2 on device valid cell name. With option transistors, enable transistors, source or drain permutations for any device recognized as a MOSFET. With option resistors, enable permutations of resistors endpoint. With option capacitors, enable permutations of capacitor top and bottom plates. Because capacitor top and bottom plates have different parasitics, capacitor plate permutation is not normally enabled. With no options, enable transistor, source or drain and resistor endpoint permutation. Another slide on comparison commands. Now these are property, set of property commands, valid cell name or device in property, valid cell name or device name, add key type tolerance. Different types of property commands are there. So with no options other than a valid cell name, return a list of triplets. Each triplet being a list of 3 items representing a property of cell. Items are in order the name of the name or key of the property, the type of the property which is one of the string, integer, double, value or expression, and the tolerance for checking which is type dependent. Note that properties of cells as opposed to instances of cells do not have values. The main purpose of property command is to establish which device properties will be compared and what will be criteria for comparison. When no tolerance value is given, then default tolerances of 0 for integer values and 0.1 or 1% for floating point values will be assigned. So there are set of property commands also, and we will see in later examples. We will use them in later episodes and we will understand how it's working. Once the LVS run and we go through the report file, we will understand what theory we have discussed here. We will understand. So thank you for watching up to this point. Don't forget to like, share and subscribe. If you have a question or query, put it as a comment. If you have a dislike, also put it as a comment. Thank you again and bye for today.